Hello. Okay, so this week we did MANOVA. So MANOVA gives us the ability to compare different groups on several outcome or dependent variables simultaneously. So we use these other than just multiple ANOVAs because it decreases the chance of the type 1 error. So using multiple ANOVAs inflates the family-wise error rate. And then we can also gather information about correlations that exist between the dependent variables. So this week I chose to look at performance satisfaction happiness scores after receiving 3 different rewards in the workplace. And reward 1 served as my control, as we'll talk about later in my contrasts. So I already installed all the packages, so I will library the packages. We need this one for type 3 sums of squares, this one for graphs, this one to look at the multivariate outliers, this one to look at multivariate normality, this one for descriptive statistics, this one to reshape the data, and then this one for robust tests, which I did not have this week. So I created my data manually. So I created a coding variable for the different treatment conditions, so group, and I specified the different levels and the number of groups I wanted and how many cases were in each group, so 3 and 12, and my labels were reward 1, reward 2, and reward 3. So next we have to create the numeric values for each of the outcome measures. So the values for performance are seen here, the values for satisfaction, and the values for happiness. So then we merge all of these variables into a data frame, which I named MANDAT. Don't know why I didn't run those as I went through them. Okay, so now it's all in one data frame. So next, we are going to create a variable for each outcome to look at the correlations. So correlations from this, and we were looking at performance, satisfaction, and happiness once again. So we run that to get the correlations. And so this reveals that happiness and performance were highly correlated at 0.9. Performance and satisfaction had a correlation of negative 0.07, and happiness and satisfaction were correlated at negative 0.77. So that meets the requirements of the data, 2 with a low correlation and 1 with a high. So next, we will get the descriptive statistics for each output, so of performance, satisfaction, and happiness. So pulling from the data, performance, and pulling from the group, and then the next for satisfaction, and the next for happiness. So we also have to check for, and obviously we can see our means and standard deviations here for reporting later. So checking the homogeneity of variance with the variance covariance matrices for each group. We take the outcomes of the data set and we split the output by group. And we indicate that we want the data from columns 2 to 4, which are the performance, satisfaction, happiness, and then we're once again splitting it by group. So 2 through 4 in group. So the results, the diagonals are, I just read it like a normal chart, but the diagonals are the variances for each outcome measure, and then the off diagonals are the covariances, which are the relationships between performance, satisfaction, and happiness. So the variance for performance are similar right here. 3.17, 3.63, 3.35. So the largest variance is only about 0.5, so between reward 1 and reward 2, which is below the threshold of 2. and the variance for satisfaction are also similar across groups. We can see satisfaction by satisfaction, 1.48, 1.70, and 1.90. And the variance ratio, the largest is relative to the smallest of about 0.05 again, or 0.5, excuse me. The variances for happiness are slightly different across groups with values of 4.3, 3.88, and 3.17. With a variance ratio of about 1, but all those are under the threshold of 2. So looking at the covariances, we can see that there's also a difference between satisfaction and performance. So performance is satisfaction. Start at the first one. Negative 0.43, 0.45, and negative 0.17. Satisfaction and happiness. So satisfaction by happiness of the negative 0.77, 0.85, negative 0.51, and then performance and happiness as well. So 2.98, 3.55, and 3.14. So that reflects the different relationships between performance, satisfaction, and happiness across the different groups. So next, to check for multivariate normality, we must create a variable for the subsets of the main data. So we're going to indicate the group, the data set, and the selected part of the data for the rows that we want to select and the columns we want to select. So for reward 1, the values are between 1 and 12, and we know they're, as talked about before, from columns 2 through 4. And we will name this reward 1. And then we will do the same thing for 2 and 3. So 13 through 24, because there's 36, so we just divide by 12. And then 25 through 36 for reward 3. So yes. We have to talk about why we used the T. So the Shapiro test needs the data to be in the format. So the variables are in rows rather than the columns, and the participants are in columns rather than rows. So we have to transpose it because we inputted our data manually. We didn't import it through Excel. So that's what this function does here, which we just combined for these other two. So now the data is in the correct format to run the Shapiro test. So to apply the Shapiro test, we just run it with the variables that we just created. So reward 1, reward 2, and reward 3. 1, 2, and 3. So the output reveals the results of the 3 tests. And obviously, as we know, if the p-value is less than 0.05, then our data deviate from multivariate normality. And it's clear that for reward 3, there's no problem because the results are not significant at 0.441. But then for reward 1 and reward 2, data deviates significantly from multivariate normality with the values of 0.01 for group 1 or reward 1, and then 0.002 for reward 2. So next we are going to look for the outliers, and we can look at the different outliers from these plots. So this is comparing columns 1 and 2. And as we see, they're all green. They're all following on the line. There's no red variables. And then columns 3 and 4. When I tried to run 2 through 4, I kept getting an error message, but I double checked to see that I had no outliers. So this works too. So next we are going to set the contrast to compare each of the treatment groups. So we're just going to set these manually and bind them to create one contrast. So reward 1, I made my control. So then we're going to compare that to reward 2 and reward 3 groups combined. So that's this first one. And then for the second contrast, we are going to ignore the control group indicated by the 0 and then compare the reward 2 and reward 3 groups. And then we will bind the contrast to create 1. and then we can run to see that these are set correctly. So 2 to 0, so we're comparing these, and then those negate each other in the second contrast. Okay. So we are going to create an outcome variable to run the ANOVA. So we have to create a variable that combines the outcomes into a single outcome. And I originally did this before I realized we had to run it twice. I did it comparing all three. So I will have 3 different MANOVAs as opposed to just the 2, just because I didn't delete it and I had already interpreted the results, so figured no harm done. So this is outcome 1 that compares performance, satisfaction, and happiness. And then the low correlation data found above was between performance and satisfaction, so I just chose that. So that's what we're going to call outcome low. And then for the high correlation data, it was between performance and happiness. So the outcome high is for that. So for each of these, as we can see indicated, that the predictors and the groups were indicated from the data. So we're going to use the outcomes that we just made, and then the predictors, and then the data frame. So this is for all of the outcomes, so performance, satisfaction, and happiness. This is for just performance and satisfaction, and this is for performance and happiness. So when you run a MANOVA, it defaults into the Pilates. And so for the first one, for these first summaries, this is just the output of the Pilates test. So this is the first one that compared all of them, the low correlation and the high correlation group. So we can look at the F ratio, and we want to look at the significant values of the F ratios. So actually, I'm going to run all these before I interpret this. So we can run the Wilks as well. So I'll run it for all 3. The Hotelling, and the Roy. So when we report, we're going to be looking at the p-values and the f-values and the degrees of freedom. So this sets all of those for us, and you will see those figures in my report. And it's important to note that the F ratios we're going to do the univariate analyses next, and that for these outcomes, it would be as if they were, we use one-way ANOVAs to conduct the measures on each of the dependent variables. So we're doing the same thing using the models created above. To look at the p-values. And the p-value in the output indicates non-significant differences between the reward groups in terms of performance and satisfaction. You can look here. performance and happiness, and satisfaction and happiness. And then the same thing for the high and low, and that compared, I can't even remember, performance and satisfaction, and then satisfaction and happiness. Or performance and happiness. Yes, performance and satisfaction for the low outcome, and then performance and happiness for the high. So all of these were non-significant. So next we are going to look at contrast. So we have to create linear models for each of the outcome measures. So I did one for performance indicated from group and the data. And before we interpret these, we don't need to, because the univariate ANOVAs we just ran were non-significant, we don't need to interpret the contrast, but I'm going to go through the process for what I would follow if the main analysis was significant. So we have to create a linear model for each outcome measure. So that's basically the same as doing the one-way ANOVA for each of the outcome measures. And so we're predicting the outcome variable from each group for each performance, satisfaction, and happiness. So then we will use these to get the contrast parameters. So the main thing, we'll do performance, satisfaction, and happiness. So the main thing that we want to look at are the values of the P are greater than the absolute value of T, and that when we compare reward 1 to reward 2 and 3 combined, there was a significant difference in performance indicated here. Looking at group 1, because that contrast was comparing groups, the combined groups 2 and 3 to the control. And we know this because it's below 0.05, but satisfaction, here, at 0.787 and happiness at 0.054 here are not significant because both values are above the 0.05 threshold. So when we compare reward 2 to reward 3, there is no significant difference in performance. Show at the top. At P equals 0.231, satisfaction at P equals 0.280, or happiness at P is 0.755. And so all those values are also above the 0.05 threshold. So if we want to go back and look at the main tests we ran, you're going to get this all in my report, but there was not a significant effect of reward on the level of performance, satisfaction, or happiness. We can see this after Shapiro-Wilks. So this is for Pillai. So our so the F value 664 at 1.74, and then the P value once again was 0.126. So I've reported all of these for Pillai, Wilks Lambda, the Hotelling's trace, and the Roy's largest root. And there was no significant different effect of reward on level of performance satisfaction. This is for the combined satisfaction or happiness. P-value for Wilks 1.73. p-value 0.13. And then hotellings, also 1.135, and then Roy's at 0.054. So we can look at the same thing for the low correlation test. There was not a significant effective reward on the level of performance and satisfaction at p-value 0.142, nor for lambdas, Wilks lambda, .14, nor hotellings, 0.138. But there was a significant effect of reward on the level of performance and satisfaction when looking at Roy's largest root at p equals 0.041. So lastly, the high correlation test, there was not a significant effect of reward on the level of performance and happiness seen. 1, 2, 3. P-value 0.066, nor for the Wilks, p-value 0.068, nor hotellings, 0.071, but there was once again, for Roy's at 0.032. So next we will do the discriminant scores for each group. So we are going to run the discriminant analysis to see how we can best separate or discriminate against a set of groups using several predictors. And that's similar to logistic regression, where there are several groups rather than two. So first we have to install that package we've already installed, and I will load it. So we have to create a new model and indicate the name of the variable in the data frame that contains the groups that we're trying to discriminate from. And then we will add the predictors as a list of continuous variables from which we are trying to make the discrimination, and it creates a formula for the linear model. And then we, of course, indicate the data set from which the values are coming, so from mandat. So I did this once again for all of them, for the low correlation model of performance and satisfaction, and then for the high correlation of performance and happiness. So we have to run each discrimination. So this is for of the models we just made. For the main model, for the low, and the high correlation. And to interpret these, we are going to be looking at the LD1 and LD2. So we're going to look at the discriminant scores, and they're the scores for each person on each variate. So the scores can be useful because the variates that the analysis identify may represent underlying constructs. So the resulting output shows each participant's score on the first and second. So we can look at the linear discriminates. So we can also, well, I guess from these we're going to look at the we're going to look at the percentage of explained variance and then the beta values. So for the discriminant analysis for performance, satisfaction, and happiness, which is the main reward one. We can look at these values and see that the first discriminant explained 77.9% of the variance, and the second only explained 22.1%. And the coefficient of the discriminant functions show that function 1 differentiated performance at here. So we're looking at the first column at 0.994. That's the beta value. Satisfaction at negative 0.285, and happiness at negative 0.592. And the second variant produced similar coefficients for performance with the beta values of negative 0.496, I guess that would be round to 3.00, and happiness at 0.865. So next we will look at the low correlation, so performance and satisfaction. So this MANOVA was followed up with a discriminant analysis, and that revealed the discriminant functions, and the first explained 91.7% of the variance, and the second only explained 8.3%. And the coefficients of the discriminant functions once again revealed that function 1 differentiated performance at beta value 0.516, and satisfaction at beta value negative 0.227. And the second variant produced the similar coefficients with beta value 0.171 and 7.35. And then lastly, the high correlation of performance and happiness. So the proportions. The first discriminant explained 78.9% of the variance, and the second explained 21%. So the coefficients of the discriminant functions once again reveal 0.990 for performance and satisfaction at negative 0.532. And then the second variant produced similar coefficients for performance at negative 0.74 or 75, and then satisfaction 1.05. Whew, okay. Last, we're going to look at the plots, and these are broken down by group membership. So the graph shows us the various scores for each person, grouped according to the experimental condition from which the person belongs. So interpreted, we look at the first variant separate from the second variant. So that's first plot, second plot, and third plot. And we split these on the axes. They're easier to see when you have shorter names, because then you can see the variants, but splitting on the axes for these, we have a few, obviously, that we can see down here, but for the clusters split in the middle, they're roughly equal on the horizontal and vertical axes. Okay, bye!